let's take a look at the structure of matter. So one thing that chemistry is very good at is chemistry demonstrates that matter is made up of atoms, and those atoms have different masses, and they have different bonding abilities and other properties. But the natural question comes, after you accept that there are atoms, is what are the atoms made of? And there was no way to really answer that question because we didn't have the technology until the late 19th century. And in the late 19th century, a scientist named J.J. Thomson discovered that inside of atoms there were small particles which carried negative charge. He discovered them, so he got to name them. He named them electrons. Now, remember, this is a time before anyone knew anything about protons or neutrons. That seems kind of strange because, we learn about protons, neutrons, electrons together. But J.J. Thomson did not know anything about protons or neutrons. He just knew that there were atoms, and inside of atoms there were electrons. So this was how J.J. Thomson imagined the atom. He imagined it as a region of positive charge. Because remember, he didn't know about protons. So he imagined that the positive charge was just sort of in this goo that was around inside of the atom. And also inside the atom, buried in that positive goo, there were electrons, these tiny little particles. And it was kind of like you imagine that the positive charge is the pudding, and the electrons are the plums buried in the pudding. So that was the model that we had at the end of the 19th century. Around 1909, there was a famous experiment that was done, and it goes by many names. Sometimes it's called the Rutherford-Geiger-Marsden Experiment. Sometimes it's just called Rutherford Experiment. Sometimes it's called Geiger-Marsden Experiment. And sometimes it's called the Gold Foil Experiment. No matter what you call it, what they did was they sent alpha particles flying in at a thin sheet of gold, and they observed what the alpha particles did, how they were deflected or scattered is the term that's used by the gold foil. So you can imagine there's a thin sheet of gold foil made out of gold atoms, and they launch alpha particles by having a radioactive source at the gold foil. Now, what they observed was that most of the alpha particles were either not deflected or they were deflected a very small amount. And that's what they expected. They expected, based on the plum pudding model that they had at the time, was that the alpha particles, which remember are positively charged, they would just sort of fly through the gold foil. What was surprising about this experiment was that some of the alpha particles were backscattered. And what that means is that they were sent backwards after they bounced off the gold foil. They came back toward the source. This was very, very surprising. Alpha particles move very, very fast, and they carry positive charges. So what Rutherford said, and he was kind of the guy in charge of this experiment, he said it was like firing a bullet and having it bounce back at you. And this was not possible if the plum pudding model was correct. So what they said was, well, if these alpha particles are somehow able to bounce back, that means that there must be some concentrated positive charge inside of the gold foil. Because if you're shooting positively charged alpha particles at the gold, then there must be some kind of positively charged thing in there that's causing them to bounce back, that's repelling them. And also, that positively charged thing that's inside of the gold, it must be very concentrated and very heavy, because the alpha particles are essentially bouncing off of it. So, they proposed a new model for the atom. They proposed that the positive charges were contained in a heavy central part of the atom, called a nucleus, and that the electrons were in the outer part. So, this way, if you sent in a fast, positively charged alpha particle, well, usually it's going to go through the outer part of the atom where there are these electrons, and it'll just pass through. But in the not too often case where you send an alpha particle in and it impacts the nucleus, or it gets very close to the nucleus, then in that case, that heavy positively charged nucleus will cause the alpha particle to bounce back. And that can only happen if the nucleus is positively charged and massive. So, that was our new model of the atom after the Rutherford experiment. Okay, so that was based on experiment, but then there's a lot of questions still remaining. Why are all the positive charges in this central heavy region? Why are the electrons in the outer region? Why don't the electrons, which have negative charges, why don't they fall in or be attracted to the positively charged nucleus? What forces are operating inside of this atom to make it look like that? Well, these answers didn't come very easily, but in the 1920s and later on, up until the present day, more and more particles started to be discovered other than the electron. The neutron was discovered. The positron was discovered. The positron is just like an electron, except it has a positive charge. Turns out this was the first antiparticle discovered. We'll talk about antiparticles a little later. Also, the muon, which is a heavier electron in a way. The neutrino, which is an almost massless neutral particle that's very hard to detect, and so on and so on. There are many, many particles out there. And so as people started to discover these particles, they started looking for patterns. What's the pattern to all of this? What forces are acting to cause these things to exist and interact? What laws govern their behavior? And over the years, over the decades, the most complete model that exists to explain the observed particles is called the Standard Model. Now, the Standard Model is not perfect. It doesn't include gravity completely, but the Standard Model is the best way that we have at the moment to explain the observations of all of these particles. And the Standard Model can be summed up this way. Everything is composed, and when I say everything, I mean everything in the universe is composed of quarks, leptons, and bosons, and their antiparticles. So let's talk about these quarks, leptons, and bosons. Well, quarks. Quarks are things that make up protons, neutrons, and some other things. And there are 6 types of quarks, only 6. And they have strange names. They were named by people in the 60s, so they have strange names. Quarks are up quarks, down quarks, charm quarks, strange quarks, top quarks, and bottom quarks. And they're represented by letters: up U, down D, charm C, strange S, top T, bottom B. These quarks are strange. Not just strange quarks are strange. All quarks are strange. They have fractional charges. So they have charges of plus 2/3 or minus 1/3. Very strange. And they are never found alone. They are only found in combinations. You only see quarks with other quarks. So for example, a proton. It turns out a proton is not a fundamental particle. A proton is made up of quarks. A proton is made up of an up quark, and a down quark. So it's often represented as UUD, up, up, down. A neutron, turns out, is made up of an up quark, a down quark, and another down quark. So a neutron is really UDD. And there are many other particles that are made up of quarks. So another type of particle in the Standard Model is the lepton. A lepton is the kind of particle that an electron is, and other fundamental particles. It turns out there are 6 types of leptons. There's the electron, the muon, and the tau. And with those 3, there's also a corresponding neutrino. So there's an electron neutrino, a muon neutrino, and a tau neutrino. The electron, the muon, and the tau all have a -1 charge, and the neutrinos have no charge. All right. And then there are bosons. Bosons are particles which convey forces between the other particles, and sometimes themselves. So the bosons carry the forces. So there are bosons that are associated with each fundamental force. The gravitational force is carried by a boson called a graviton. The electromagnetic force is carried by photons, which we've seen before. The weak force is carried by 3 particles, 3 types of bosons called the W+, the W-, and the Z0 or Z0. And the strong force Remember that strong force, that's the binding force in the nucleus. The strong force is carried by a boson called a gluon, which makes sense because it glues together nucleons. So let's go through some of the details of this. Those are the fundamental particles in the Standard Model. And we have a couple names, a couple terms that you need to be familiar with. Any particle made up of quarks is called a hadron. So if something is made up of quarks, it's a hadron. A hadron, which is made up of 3 quarks, is called a baryon. So protons and neutrons are baryons, because a proton is made up of an up, and a down. A neutron is made up of an up, a down, and a down. 3 quarks, that type of a hadron is called a baryon. Now, there are also hadrons that are made up of a quark and an antiquark. This type of particle is called a meson. So, for example, there is a meson called a pi plus, and a pi plus particle is made up of a quark and an antiquark. It's made up of an up quark and an anti-down quark. That's the antiparticle of a down quark. So the way that this is represented is we have an up quark and an anti-down quark. The way that you represent an anti-down quark is D for down, and to show that it's an antiparticle, you put a bar over it. All right, so what's the deal with these antiparticles? Let's talk about that. Turns out all quarks and leptons have antiparticles. Antiparticles are identical to particles, but they have opposite charge. So they have the same mass, but they have opposite charge. And a few other details are different, which we're not going to discuss. One thing that's strange about antiparticles is that if a particle interacts with its antiparticle, they annihilate. And what I mean by that is they destroy each other and turn into energy. All right. Antiparticles are represented, and you've seen this, with bars over them. So an up quark is U. If we have an anti-up quark, that's a U with a bar over it. An electron neutrino would be a nu. An antineutrino, or anti-electron neutrino, would be a nu with a little bar over it. If we have a proton is made of an up, and a down. If we have an antiproton, it's made of an anti-up, and an anti-down. Now, bosons do not have antiparticles. They are a different category. Each boson, and bosons are also called gauge bosons, but each boson conveys a different force between certain particles. So I mentioned that the graviton carries gravity, or conveys gravity. It conveys gravity between any particles which have mass. So a graviton is responsible for gravitational forces between any particles that have mass. The W+, W-, and Z0 particles, or bosons, convey the weak force, and they can only convey that weak force between quarks and leptons. So those particles do not convey forces between bosons. They only convey forces between quarks and leptons. Photons convey the electromagnetic force between charged particles. So the photon will not interact between, or will not convey a force between 2 neutrinos, because those neutrinos do not have charges. You have to have charges, or you have to have particles with charge in order for photons to convey an electromagnetic force. Gluons convey the strong force between quarks and other gluons. Now, there's a lot going on here, and keep in mind, this took many decades to develop, so we're trying to address it in just a couple of minutes. But there are laws that govern the behavior of all of these particles. There are conservation laws. Just like there's mass and energy conservation and charge conservation, there are other things which are conserved in particle interactions. Turns out, lepton number is conserved. Now, what the heck is lepton number? Well, a lepton has a lepton number of 1. If you have an anti-lepton, so like an anti-electron or a positron, that has a lepton number of -1. And all other particles which are not leptons, so quarks and bosons, they all have lepton numbers of 0. Okay. Baryon number is conserved. What the heck is baryon number? Well, quarks have a baryon number of 1/3. Antiquarks have a baryon number of -1/3. And all other particles, so leptons and bosons, they have baryon numbers of 0. And there's also a quantity called strangeness. And just like it sounds, strangeness is weird. Strangeness is conserved unless it's a weak force interaction. And we'll try to address this a little bit later. But strange quarks have a strangeness number of 1. Anti-strange quarks have a strangeness number of -1. And every other quark, lepton, and boson has a strangeness number of 0. Okay, let's see how these conservation laws work. Let's say we have this interaction between two particles. We have a proton that interacts with an electron, and after they interact, we're left with a neutron and an electron neutrino. According to the conservation laws, charge should be conserved, lepton number should be conserved, baryon number should be conserved, and strangeness should be conserved. Mass energy should also be conserved, but we're not going to worry about that right now. So let's see, is charge conserved in this interaction? Well, before the interaction, we have a charge of +1 and -1. So that's a total charge of 0 before. And after, we have a charge of 0 and 0. Okay, so we start with a charge of 0 and we end with a total charge of 0. Charge is conserved. Let's look at lepton number. Okay, well, the lepton number of a proton isn't a lepton. It's made up of quarks. So the lepton number of a proton is 0. Lepton number of an electron is 1. Okay, so we begin with a lepton number of 1. In the end, we have a neutron and an electron neutrino. A neutron has a lepton number of 0. Electron neutrino has a lepton number of 1. So we end with an we end with a lepton number of 1. So we start with a lepton number of 1. We end with a lepton number of 1. Lepton number is conserved. Baryon number. We start with a baryon number of, a baryon number of 1. The proton is made up of 3 quarks, each with a baryon number of 1/3. So 1/3 plus 1/3 plus 1/3. And then the electron has a baryon number of 0. And we end with a neutron and an electron neutrino. The neutron has a baryon number of 1/3 plus 1/3 plus 1/3. And the electron neutrino has a baryon number of 0. So we start with a baryon number of 1. We end with a baryon number of 1. And strangeness, well, there's no strangeness to begin with, and there's no strangeness at the end. So strangeness is conserved. It starts with a strangeness number of 0. It ends with a strangeness number of 0. Okay. Now, one way to depict these interactions between particles is with something called a Feynman diagram, named after Richard Feynman, a famous physicist. It's a way of depicting particle interactions. Now, this can be a little tricky because in IB, time is usually on the vertical axis in these diagrams, but that's not always true, so you have to be careful. You have to make sure you look at the diagram carefully to determine which way time is moving. But, no matter what, in Feynman diagrams, the particles are represented with arrows, and the arrows go forward in time for particles and backward in time for antiparticles. Now, don't read too much into this. That doesn't mean antiparticles are traveling backward in time. It's just the way that we draw these diagrams. The bosons, they are represented in these diagrams with dotted lines or wavy lines. And only 3 particles, antiparticles, or bosons can meet at a vertex or a connection. So those are the rules. Now, I'm going to show you an example of a Feynman diagram, and we're going to have time going along the vertical axis. So we start out with a neutron, and I'm going to draw a vertex here. And at this vertex, the neutron is going to split into a proton and a W- boson. Notice that the W- boson is going to be represented with a dotted line. Then the W- boson is going to go off, and at a vertex here, the W- is going to become an electron and an antineutrino. Now let's see what this represents. If you go down to the beginning is down at the bottom of the diagram, when time is at its lower value. At the beginning of the diagram, we started out with a neutron. What this diagram is representing is that the neutron then split into two particles, the proton and the W- boson, and then the W- boson split into two other particles. So in the end, at the end of the diagram, we ended up with a proton, an electron, and an antineutrino. The way that we would say this is that this shows a neutron decaying into a proton, an electron, and an antineutrino, where the W- boson mediates the decay. That's the terminology we use. The W- boson, it was just there for a brief time. It mediates the decay. The W- doesn't exist at the end. It's a temporary particle. Now notice, at every vertex, all of the conservation laws have to apply. Now I'm not going to go through that, but if we applied the conservation laws at this lower vertex, where the neutron became the proton and the W- boson, all the conservation laws of charge conservation, mass conservation, lepton number conservation, baryon number conservation, strangeness conservation, they should all be true at that vertex. And they should also be true at this second vertex, where the W- decayed into the electron and the antineutrino. Now, I can draw a different diagram. Let's say that we have a proton and an electron, and we have this happen. What this is showing, and again, time is going on along the vertical axis, this shows a proton and an electron interacting and resulting in a neutron and a neutrino. And again, we would say there's a W- in there, and that W- only exists briefly. The W- mediates the interaction between the proton and electron. Also, again, at each vertex, charge, lepton number, baryon number, strangeness, and mass energy are all conserved. So that's Feynman diagrams. Now, last thing I'll mention is the Higgs boson. The Higgs boson is part of the Standard Model, and it's a very recent topic of conversation because this boson was recently discovered. It was discovered in 2013, and it was a prediction of the Standard Model. So no one had observed the Higgs boson until 2013, but many, many years before, the Standard Model, if you look at it enough, predicts that the Higgs boson should exist. And so that was considered a big success of the Standard Model and a big piece of evidence for the Standard Model. It is a boson, this Higgs boson, of course, it's a boson. It's a boson. It interacts with other particles to give them or imbue them with mass. And it's a very strange idea, and we're not going to go too deep into it. But one big idea to know about the Higgs boson is that it was predicted by the Standard Model, and when it was actually discovered, that was a big piece of support for the Standard Model.